wanted to discuss a convenient way of handling the solution to a straight line fit, to find the best fit parameters of the slope and the intercept, to find the uncertainties on the slope and the intercept and their correlation. It's a convenient way for Python programming, or it's a convenient way for programming in general, and it uses matrices and vectors. So let me describe the procedure, and let me describe the procedure by starting by introducing a couple of vectors and a matrix. And then we're going to solve for the best fit slope, best fit intercept, and the uncertainties in terms of these vectors and matrices. So the vectors and the matrices are built out of the independent variable, the dependent variable, and the parameters of the fit function. So y here is a vector, and it contains the dependent variable as the elements of the vector. So y1, y2 through yn. M is a matrix. It is a two-column matrix. The first column in the matrix is the independent variable, so x1, x2 through to xn. And the second column in the matrix is just an equal number of ones. So that's the matrix M. And then finally, the vector P is just a two-element vector. It contains the two parameters. It contains the slope M and the intercept C. So if you look at these three new quantities I've introduced, the vector Y, the matrix M, the vector P, they contain the dependent, independent variables, so the xi's, yi's. They contain the fit parameters, slope and intercept, M and C. In terms of those vectors and that matrix, we can write down a vector matrix form for the relationship between the dependent, independent variables and the fit parameters. And it's simple and straightforward to write down in this language. It's just this equation here. So that this vector of dependent variables equals this product of the parameter vector with the matrix containing the independent variables. You can understand this. You can picture this. If you just imagine multiplying the top row of the matrix by the vector that contains the parameters. So you'll get M times x1 plus C. And that will equal the dependent variable y1. And so you see that this matrix form of the relationship between all the measurements of the independent variables and dependent variables and the parameters of the fit function holds. Okay, so now we've seen that we can write the relationship in this new fashion here, in these using these top two lines. I'm just going to rearrange this expression, rearrange it to solve for the parameters P. So these next two lines here are just me solving for the parameters P. And it's just really two basic steps involving actually matrix multiplication. So the first step is that I'm going to multiply both the left-hand side and the right-hand side of this vector matrix equation by the transpose of M. If you remember, the transpose of a matrix involves reversing the columns and vectors. So the transpose of a matrix involves reversing the rows and columns. The rows become the columns and the columns become the rows. And so I'm just multiplying by the transpose of M. I'm multiplying on the left-hand side and I'm multiplying on the right-hand side. Next step. Then I multiply again the left-hand side and the right-hand side by this quantity here. So this is the inverse of the product of the transpose matrix and the matrix itself. So I'm going to multiply the left-hand side and the right-hand side by this new matrix. When I do that on the right-hand side of this equation here, what's going to happen? I've got now the product of the inverse of the product of the transpose and the matrix with the product of the transpose and the matrix itself. And so this is going to give me the unit matrix. And so this just cancels out on the right-hand side here. So it's just going to give me the vector that contains the fit parameters, the slope and the intercept. And then on the left-hand side of this equation, what I'm going to see is the product of this inverse, the transpose of the matrix, and that column vector involving the dependent variables. And so this is the solution to my problem. I can calculate the parameters of the straight line fit to the data, the two elements of this vector P, by just simply carrying out this product of these matrices with the dependent variable y, with the vector containing the dependent variable y. And so this is all I'm going to do in solving the straight line fit on the computer with my Python code. I'm just going to carry out this one line, this one calculation here to find out what the best fit parameters are. Now, I'm not defining here how we calculate the errors on the best fit parameters. I'm not deriving here how we calculate the errors on the best fit parameters, and also the correlations between the two parameters. You can prove that in a similar way. As I say, I'm not proving it, but let me just write down the solution for the errors. So this matrix C is what we call the covariance matrix. It's a 2x2 matrix. The diagonal elements of this matrix C are the one in the top left is the variance, that's the square of the standard deviation, the variance of the slope, so that's going to tell us the uncertainty in the slope, and then the other diagonal downstairs in the bottom right, that's the variance, the square of the standard deviation for the offset parameter, and so that's going to tell us the uncertainty in the offset. The off diagonals here, they have a symmetry. They're equal. So this off diagonal upstairs on the right is going to be the same as this off diagonal downstairs on the left, and they are the covariances between those two parameters, between M and C. And so this simple matrix here contains all the information about the uncertainties in the best fit parameters, and you can show that it's equal to the uncertainties in the data points. So that's the sigma y squared, that's the variance in the data points, multiplied by this inverse of the product of the matrix M and its transpose. And so that yields, this equation yields the uncertainties that are associated with your best fit parameters. And so if you want the uncertainties associated with your best fit parameters, you just use this second equation here. So look, this is really fantastic. When you're implementing your Python code to do the straight line fit to your data, you just need this equation for P for your fit parameters, this equation for the covariance matrix C for the uncertainties related to those fit parameters. It's as simple and straightforward as that in this vector matrix language. I just wanted to ground you a little bit in the explicit forms of these quantities that we need to solve for the best parameters and the uncertainties in the best fit parameters. So on this slide, I've just documented the various quantities that we used on the previous slide. So if you remember, there was the matrix M and its transpose. There was, importantly, a product of the transpose of the matrix with the dependent data, with the dependent data vector. And then there was also, importantly, the product of the matrix and its transpose, and the inverse of that product of the matrix and its transpose. And I've written all of those quantities down here. So upstairs here, I'm reminding you of what the matrix M is. Remember, it's a two-column matrix. The first column is the independent variables, x1, x2 through xn. The second column is just the corresponding set of ones. Its transpose, you want to think about its transpose, you just got to reverse the rows and the columns. So the transpose is now a two-row matrix with n columns. The independent variables are in the first row, then the set of ones, n ones, is in the second row. If you multiply the transpose by the vector containing the dependent variables, and that's what I've explicitly written out here, this product of a vector with n elements multiplying a two-row n-column matrix gives a vector that just has these two elements here. So this product is just this little column vector here with two elements. You might remember that we saw this in our first derivation of the best fit values of M and C. Downstairs here, I've written out explicitly the product of the transpose of the matrix and the matrix itself. So again, that's the product of a matrix that has two columns and n rows on the right here, with a matrix that has two rows and n columns. If you imagine multiplying this out, for example, taking the left-hand column here and multiplying the top row here, you get four terms. You get a 2x2 matrix, and this is the 2x2 matrix. And you might remember seeing this matrix when we originally solved the problem of the best fit parameters explicitly. And then finally, the only other combination that we use in solving for M, C, and their uncertainties is the inverse of this product of the matrix and its transpose. And I've written this down here. You can calculate the inverse by calculating the adjunct of a matrix, a joint of a matrix, and dividing by the determinant. And I've written out the result of that explicitly here. And actually, this might be familiar to you also. This matrix here, this 2x2 matrix here, we saw before when we talked about the uncertainties in the slope and the offset and the correlation between them. Finally, I want to show you my code in which I implement a straight line fit of data related to the expansion of the universe and of Hubble's law and Hubble's constant, using this formalism, this vector matrix formalism, for calculating in just one equation the best fit parameters, and one equation the various uncertainties associated with the best fit parameters. So let's just walk through the steps in this, and I think you'll see, I think you'll be able to visualize how introducing these matrices and vectors is kind of a handy way of solving, a convenient way of solving this problem. Okay, so in this first cell, I'm just importing the libraries that I need. I just need to do some plotting to show you the data. So I want matplotlib. I just need numpy because we're going to use that for some of the matrix algebra. I've got to take transposes, I've got to take inverses, I've got to take products, and we're using numpy for that. I'm also going to import a file from my Google Drive that contains a data set of Hubble data. Basically, it's a data set of redshifts of galaxies versus distance to galaxies. And it's that we're going to fit, because it's that data that shows the expansion of the universe. It's that data that fits to a straight line where the slope is actually related to the Hubble constant. It's actually the inverse of the Hubble constant in the way that I'm going to fit it. It's actually the age of the universe in the way that I'm going to fit it. Okay, so second cell here. Second cell here, I'm going to do a couple of things. I'm going to read in my file from my Google Drive that contains the data. My file contains two columns. One is the relative redshifts, a proxy for the recession velocities of the galaxies. And the other column is the distance to the galaxies, determined by these standard candles, these stars, bright variable stars that can be used as standard candles. And so if I execute this cell, I read in the file, and then I'm going to strip out for my independent variable, the first column, that's the redshifts. I'm going to strip out for the second column, I'm going to strip out the distances to the galaxies. So those are my X and Y, my independent and dependent variables. I also want to know the size of the data set, the number of galaxies that I have. And so I just grab the size of either the dependent or the independent variable. And then finally, I just want to see the data, check the data. So I'm just plotting the data here. X again is the fractional redshift, the proxy for the recession velocity of the galaxies. Y again is the distance to the galaxies, the radial distance to the galaxies attained from these standard candle stars. And so we can look at this plot. Horizontal axis, fractional redshift. Vertical axis, distance to the galaxies. You see that downstairs here in the bottom left corner, if the galaxies are close, galaxies are nearby, then there's little redshift. But as the galaxies get further away, then the redshift, the recession velocity systematically increases. And so you see here the evidence of the linear relationship, the proportional relationship between distance from us and recession velocity of the galaxy. Just a note on the units here, in this plot of Hubble's law, this fractional redshift, that's actually unitless. It's the change in the wavelengths divided by the wavelength of the particular spectral line. This vertical axis here, this is in parsecs, and the closest star is about a parsec. Okay, third cell. So third cell, I've already defined a vector that contains the dependent variable y. I need a matrix M that contains the independent variable. And so the first thing I'm doing is defining that matrix that we called M. So I'm using this particular function in NumPy. It's very handy for this particular task. It builds a matrix M out of a sequence or stack of columns. And the arguments to this function are the vectors that contain the data for each column. Now I got two columns. One is the independent variable. So here's the independent variable X. And the other one is just a corresponding set of ones. And so that here is the vector of the array containing a corresponding set of ones. And so this simply builds my matrix that I need for this scheme for solving for the parameters and their uncertainties. Now, to solve for the parameters and their uncertainties, I need not just this matrix, but I need its product with its transpose. I need the inverse of that product with its transpose, and I need the product of the transpose of the matrix with the vector containing the dependent variable, the quantity y. And so these three quantities, variables that I need, are calculated here. Now, specifically, I'm using NumPy and some linear algebra tools that are available in NumPy. So you'll see downstairs, I use the function dot that it can multiply vectors. It can multiply vectors with a matrix. It can multiply matrices together. And so I'm using that for the products that I need involving vectors and matrices. You'll see downstairs here, transpose. So I need the transpose of the matrix. And so I'm calling a NumPy function that calculates the transpose of the matrix. And also you'll see downstairs inverse. I need the inverse of a matrix. And so I'm using, again, a NumPy function that allows us to calculate the inverse of a matrix. So let's just walk through them. This first statement here, this is just multiplying the matrix M with its transpose. So I'm using the transpose function here, and then this dot function is multiplying these two matrices together. This is going to give me this 2 by 2 matrix. Second row, second statement here. This is just calculating the inverse of the result from the previous statement. So here's the result from the previous statement, this product of the matrix and the transpose, and I'm just calling the function inverse with that as the argument to calculate the inverse matrix. And then finally, this third statement here, I want the product of the matrix M, or the transpose of the matrix M, with the vector y. And so again, I'm using this function dot to carry out the products. This time, the two arguments are the transpose matrix and the vector y. And so let's just run this cell. And downstairs here, I can look at the results of those three calculations. The product of the transpose matrix and the vector y, and if you remember, the transpose matrix has 2 rows and n columns. The vector y is a n column vector. If you multiply those together, you just get a 2-element vector. And here's that 2-element vector. I've just printed it out for us to see. It is a 2-element vector. The product of the transpose matrix and the matrix itself. So this is a product between a 2-row n column and an n column 2-row matrix. That gives a 2 by 2 matrix, and I'm just printing that out here. And then finally, the inverse of that 2 by 2 matrix, it's also going to be a 2 by 2 matrix. And I've just printed that out here. So this is just me checking the results of this matrix vector algebra involving transposes and inverses and products make some sense. So now we've got these three tools. It's simple for us to actually go ahead and calculate the parameters and the uncertainties. And so that's done in this final cell here. The parameters are obtained by multiplying the inverse of the product of the transpose and the matrix M by the product of the transpose of the matrix and the vector Y. And we've calculated these two ingredients, so we just need to multiply them together. This gives us a little vector that contains the two best fit parameters. One is the slope and one is the offset or intercept. We want to calculate the uncertainties on those quantities. The first thing we actually need to do is determine the uncertainties on the data points. So this line here, in this particular problem, I didn't quote uncertainties on the data points. We're going to calculate the uncertainties on the data points from the variation of the data points from the best fit. And so you do that calculation. We discussed doing that calculation by calculating the chi-squared. That's the sum of the square of the residuals. So it reflects how close or far the fit is from the data points. And then if you divide that by n minus 2, the number of data points minus the number of fit parameters, it's what we call the number of degrees of freedom. That gives you the average variance of each data point. And so the square root of that would be the standard deviation we're associating with each data point. So this quantity here, this line here, the statement here calculates sigma y squared, the variance of the data points, based on the scatter between the data points and the fit function. Once we got these variances, then it's a simple matter to calculate the uncertainties on M, C, slope, intercept, and their correlation by simply multiplying the variances of the data points by, again, this product that we've already calculated is the inverse of the product of the transpose matrix and the matrix. And so this one cell here, I love this, just calculates the two fit parameters. Here they are. 4,500 roughly is the slope. Minus 12 is the intercept, very close to 0. The variance of the data points, so it's the square of the standard deviation. It's just a number, okay? And that reflects how much the data points are scattering from the best fit line. Is this number here, 653. If we took the square root of that, it would tell, it must be around 25 or something. It would tell us typically how much a data point is from the fit function, from the straight line. And then finally, here's the 2 by 2 matrix, the covariance matrix, which contains in the top left the square of the uncertainty on the slope, bottom right, the square of the uncertainty on the intercept, and then on the off diagonals, they're equal and they reflect the correlation between the slope and the intercept. So we can calculate the best fit line and plot the best fit line against the data points. And I've done that in this cell here. To obtain the best fit line, I just used this equation here. This was our starting point in our vector matrix formulation of this straight line fit problem. We said that, remember we said that we could write the relationship between the dependent variables, the independent variables, and the parameters as this particular product. It's the product of the vector the matrix M, which contains the independent variables, and the parameters M and C in a little column vector. And if you multiply those two together, then you get the dependent variables. And if I do it for the best fit parameters, I get the best fit dependent variables. And so I get the fitted values of the for the fit function versus the independent variables that I made the measurements at. I called this fitted value df for some reason that escapes me now. Anyway, on the plot, I'm now plotting two things. I'm plotting the data points in magenta again, and then I'm plotting my best fit straight line. It's this green line here. It's obtained from this calculation here. And you see that the straight line, the straight green line, basically goes through the data. You see that there's some scatter of the data about the straight green line. We said that that scatter is about 25 typically, and it looks like it's probably like that. There are data points that are closer, but there are some data points that are quite a bit further away. So I think that scatter makes sense. Anyway, I wanted to show you how to implement that vector matrix formalism or algorithm for doing a linear least squares fit, calculating the slope, calculating the intercept, calculating the uncertainties in those parameters. With this example, that is perhaps the most famous case of a straight line fit that showed the expansion of the universe and allows you to determine the age of the universe.